Good evening. Welcome to everyone. I'm Frances Hellman. I'm chair of the physics department, and it's my pleasure to welcome you tonight to the annual Emilio Segre lecture. Our lecture tonight actually has two purposes. In addition to the annual tradition of bringing in a great experimentalist to tell us about current important things in physics, we are also using this opportunity to introduce a commemorative award in honor of Livingston and Lawrence, and so I have people from the APS here to do that. So I'm going to start by introducing my distinguished visitors from the American Physical Society, and then we'll come back and tell you a little more about the Segre lecture. So the people from the American Physical Society, I have both Cherry Murray and John Wigden. Cherry Murray is the Deputy Director for Science and Technology at the Lawrence Livermore National Laboratory. She is the upcoming President of the American Physical Society. She's also an extremely distinguished scientist, nationally recognized for her work in surface physics, light scattering, and complex fluids. She's a member of the National Academy of Sciences, the American Academy of Arts and Sciences, and in 2002 was named one of the 50 most important women in science by Discover magazine. She's also somebody I've known for quite a while and have never had the honor of collaborating with her, but I've known of her work for many years. We also have here John Wigden, who is currently an honorary professor of physics at Washington University in St. Louis. He is chairman of the History of Physics Forum of the American Physical Society. His scholarly work has been in the areas of molecular physics and the history of science, and his professional activities include being editor of the American Journal of Physics, the Director of Development at the National Science Standards Project at the National Academy of Sciences. He's authored and edited many books, including The Physics and the Sound of Music, and Most of the Good Stuff, Memories of Richard Feynman. John Wigden is a fellow of the American Association for the Advancement of Science and the American Physical Society. So I'm going to have our two American Physical Society representatives explain to us the significance of this plaque and both introduce the Chancellor and go through a ceremony in honor of this plaque.
Thank you, Francis. So I'm Cherry Murray. I'm actually going to be president of APS in 2009. So this is... Hello? Is that better? Okay. I'll actually be president of the American Physical Society in 2009. It's a long, involved process, starting with vice president, going to president-elect, then president, then past president. And Artie Bienenstock is going to soon be president, and I will soon be president-elect. And I actually have the honor to introduce John, who you already heard his credentials. He's going to tell you a little bit about why his committee, he's chair of a committee for historic sites in physics, chose Berkeley and Old LeConte Hall.
Thank you very much. The committee to name historic sites was initiated about 2 years ago, 2005, early 2005. It's a very good committee. Let me tell you, there's Gordon Boehm from Illinois, Catherine Gebbe from NIST, Gerald Holton from Harvard, and Steve Weinberg from Texas are on the committee, in addition to myself. We've named roughly 15 sites so far in the, well, it's actually 3 years. Let me just give you a sort of a feel. Some of you may know the name Henry Rowland at Johns Hopkins, who created diffraction gratings that really revolutionized atomic spectra. And these gratings were bought by laboratories all over the world. Michelson-Morley at Case, with the famous Michelson-Morley experiment. Ben Franklin and the Franklin Institute. Bell Labs. Bell Labs. Cherry Murray used to be at Bell Labs for some time in a director of physical science research, right? And so Bell Labs, though, was where the transistor was born and has changed our lives. Well, and one of the ones I'm most proud of. And here comes a quiz. Some of you know, many of you know, that self-inductance was discovered by Joseph Henry. And the unit of inductance is a Henry. Now, here's the quiz. Where was Joseph Henry? No, wait, don't say it. If you think you know, raise your hand. 2 people, I don't know. Well, where was he? No, Princeton's wrong. You flunk. No, the reason I would be proud to give something to Princeton. They'll get theirs. This one went to the Albany Academy, a high school in Albany, New York, where Joseph Henry, teaching 11 months of the year with only August to do his research, discovered self-inductance, and he was right on the verge of it. One August, had to shut down, wait for 11 months until the next August to continue his research. I'm very proud to have given the Albany Academy and made it part of the Register of Historic Sites of the American Physical Society. So there's a number of these sites now, and the most recent one, and the one we're here celebrating tonight, is Berkeley for Ernest Lawrence, Stanley Livingston, and the cyclotron. So now there's 2 parts of this. Sherry Murray will take the honor of presenting the plaque, and I'll give it to her. And then there's one other part which I'll come back for.
All right. I think at this point, Bob, why don't you come forward? And what this says, which will go on the old LeConte building, is, in fact, it's pretty heavy. Very heavy. At this site, Ernest O. Lawrence invented a new type of particle accelerator, and in 1930 to 31, he and Mr. Stanley Livingston built the first successful cyclotron. With this cyclotron and its successors, the University of California, Berkeley became a major center for nuclear and particle physics. Historic Physics Site, Register of Historic Sites, American Physical Society. And I would also say that with the cyclotron, the age of big physics was born. And Berkeley is at the heart of it. And it's wonderful that we could have Burt Richter talk about big physics and what's the future of big physics. So we're back. I think you can put that down so you can, it's heavy. It's really heavy. Now, Bob must sign the official ledger.
So before, should I sign? No, I just want to thank the American Physical Society and John and Sherry specifically for this, the first of what I suspect will be several plaques which will come to Berkeley, because this is just one of a number of historic discoveries that were made here. I know your criteria are high, but so is the quality of our physics. And it's also a particular personal pleasure. I mean, first of all, Sherry and I first met when she was a graduate student in the hallways when I was first setting up my lab at MIT. And Burt Richter and I have been friends for a very long time, and it's great to have the privilege of hearing Burt talk. And I also want to recognize both Francis and Dave Jackson. Dave, where are you? There he is. Who put in a tremendous effort to ensure that this would indeed take place. And so we're really grateful to Dave also for the role that he played in this. Thank you.
The official historical record of these is this lovely leather-bound ledger that has pictures and so forth. You'll have pictures in here. And both presenter, in this case Cherry Murray, and the receiver signs the ledger. So Cherry, why don't you sign here? Gaia. Thank you very much, and this concludes the 11th site. A few more have been named, but they haven't been presented yet.
Great. And I really do want to thank the people who put the original nomination together, which was largely Dave Jackson, who's already been mentioned back there, and I know Chancellor Bergeneau, and actually my predecessor, Marjorie Shapiro, I think. And so I'm really grateful to the efforts they put in to bring this plaque here. So one more round of applause for the people who made that happen. Okay, so let's turn now to the Segre lecture, and I give you a little bit of background on the lecture. These lectures began in 1987, thanks to the generosity of the Raymond and Beverly Sackler Foundation. Their vision was to honor the great work of Nobel laureate Emilio Segre, who was on the Berkeley faculty from 1938 until his death in 1989. And his vision was bringing world-class physicists who can make their work accessible to a public audience. And it's a tremendous honor to me to be able to have brought to Burt Richter here tonight. He is both a world-class physicist and also a Nobel laureate, so very much in the tradition of Emilio Segre. He is a senior fellow at the Spogli Institute for International Studies. He's a professor at Stanford University, and he's the former director of the Stanford Linear Accelerator. He's best known for his discovery of the psi particle, sometimes called the J psi particle, or the psi, I guess J psi is accurate. Is that? The announcement of this discovery helped usher in a new era in high-energy physics, and he was awarded the Nobel Prize for that work in 1976. He's a member of the National Academy of Sciences, a fellow of the American Academy of Arts and Sciences, and of the American Association for the Advancement of Science. He's also a past president of the American Physical Society, so we have quite an illustrious group of people here from the APS tonight. In addition to his many research, and there is many, the Nobel Prize represents a small piece of a very long and illustrious research history, and administrative contributions. He has served on many advisory committees to governments, laboratories, and universities, including committees which have been most recently focused on the crucial topic of energy production and conservation. I've served with him on some of these committees, and I can speak to the fact of how difficult it is to bring a group of faculty members together to agree on anything. It has been likened to herding cats, and Burt Richter is one of the best people I have ever seen at herding cats. So with that introduction, I'm very proud to introduce our tonight's speaker, who is going to be talking about elementary particle physics, a personal look ahead.
Thank you, Francis. It's a pleasure to be here. And now that it's a pleasure to be here, I have to figure out how to get this thing off and get the next thing on. It's a great, don't worry. We're going to get there. There we go. We had a very nice reception before this. I observed to Francis that I didn't see any of the young people there, and I got a promise that next year, at least the postdocs are going to all be invited to the reception. I had very good food, by the way. I think that now that you have this award for the cyclotron, it might be very useful to show you what a cyclotron looks like, because most of you have never seen one. This is the first Lawrence cyclotron. This cyclotron was 4 inches across, and it ushered in a new era in physics. It was built, I think, in 1930, and in the next year, the 11-inch cyclotron was built. It broke the 1 MeV barrier in 1932. It wasn't the first accelerator to reach 1 MeV. The Cockcroft-Walton generator had reached it before, but it was a scalable one, and none of the others were. What you see is a rapid expansion of big-time science as they went first to the 60-inch cyclotron, which is in the upper left, then to the 184-inch cyclotron, which is in the middle, and then the cyclotron era ended and it went to a different kind of machine, which I'll say something about in a minute. Right now, the three biggest cyclotrons in the world are one at the Paul Scherrer Institute in Switzerland, one at Michigan State University with a superconducting cyclotron, and one at the University of British Columbia. All those things are between 500 MeV and a GeV, and they're all close to a megawatt in beam power. The cyclotron era ended because cyclotrons weren't scalable. If you take a look at a cyclotron, what you have, is there a laser pointer or something around here? We'll just keep talking. What you have is a magnet, and then the particles spiral around and around, gaining energy on each turn and going out and out and out. If you look at how you make these bigger, the mass of the system scales with the cube of the energy. The whole thing's got to get bigger in all dimensions. You saw the 184-inch cyclotron. That clearly couldn't go on, and it was replaced with what's in the lower picture. That's the synchrotron, where as the particle energy goes up, the magnetic field goes up, and everything stays in the same orbit, and that scales as the first power of the energy. So it's all you have to do. All you have to do is make the radius bigger as it goes. Interestingly enough, the synchrotron also comes from Berkeley. Ed McMillan here and Wechsler in the then Soviet Union are the inventors of the synchrotron. So maybe there can be a postscript to the plaque and sort of a mini plaque underneath. Let me turn now to what I'm supposed to be talking about here tonight. I said I was going to give a personal view of what's important to do in particle physics. And if you read the abstract, I started it off with, I have two. See if I can make either of them work. Oh, that's a better one. I started it off with the Tale of Two Cities. It was the best of time, it was the worst of time. It's the best of time because particle physics has been turned upside down with the discoveries of the last 15 years, and I'll talk a little bit about those. It's the worst of times, at least here in the US, because all our big accelerators are shutting down before the next generation of big accelerators is ready to be built. And so the US, which has led the whole business for many, many years, is no longer on the frontier. I said also in the abstract that this is a time of tight money, and what we have to do are the things that are really important rather than the things that are only really interesting. So my list of really important is what's going on in the energy frontier. There's a new one coming on in Switzerland, the LHC. There's a new one under discussion, which is one for after that, and the hope there is that that will be built in the US. There's accelerator R&D, because these accelerators are getting so expensive. If we don't have some kind of breakthrough that reduces the cost per unit energy, we're soon going to run out of the ability to afford them, not the ability to build them. Next on the list is dark matter and dark energy. What are they? It was only 10 years ago that the whole physics world was startled with the supernova probe experiment, coming to the conclusion that 75% of the effective mass in our universe was something we knew absolutely nothing about. Given the name dark energy, we still don't know what it is. And 20% of it is dark matter, and we don't know what that is either. And it's only 5% of the matter in the universe is us. That's a little bit humbling to think about. There's 95% more out there. I don't know what dark matter people look like, but they interact with us only weakly, so perhaps we'll never know. So let me start off with going down a few of these things. I want to start with the biggest machine. That's the Large Hadron Collider. Soon to come on at the CERN laboratory in Geneva, Switzerland. I think you can see the outline of the machine there, going around in the Swiss countryside. There's a Geneva airport over there. This is a 27-kilometer in circumference machine. It's a proton-proton colliding beam machine. Colliding beams are what has replaced all the fixed target experiments in particle physics. Colliding beams give you energies and reactions that relativity says you simply can't get with beam incident on a particle at rest in the laboratory. So underneath the Swiss countryside is this 27-kilometer tunnel. It had an electron-positron collider in it. I'll come to those in a minute. That was turned off in, I think, early 2000. And the magnets for this 7 by 7 TeV machine were put in there, and that machine is nearing turn on. Here's a view in the tunnel. You can look in the distance and see the gentle curve bending around. This tube contains, each tube contains 2 superconducting magnets. The beams are going in opposite directions, and they're fixed to come into collision at 4 points around the machine. Not only is the machine huge, but the detector is huge also. This is one of the 2. This is a detector called Atlas, and to give you a scale, that's a person standing there. This thing is enormous. So is the other detector, which is for some reason called a compact detector, but it's nearly as big as that one. This is a scale with Atlas shown over a 6-story building. Now, the person who's the leader of the Atlas collaboration was a postdoc with me, and he worked with me on the sphere colliding beam electron-positron experiments. And it's sort of interesting to look at the detector that he cut his teeth on in doing his first experiments with colliding beams. Atlas is bigger than a 6-story building, and that little thing is the Mark I detector. We did a lot of very nice physics with the Mark I detector. The LHC is supposed to be completed sometime in the first half of 2008. That'll be the completion of the installation of the machine and the detectors. The second half will begin full operations to commission the machine and calibrate the detectors. This is all very big, very complicated stuff, and I think that it's going to take a little while to get these things settled down and get them running right. And I have to get rid of a surplus of paper. If this new machine reaches a few percent of its design intensity, it will find the Higgs boson. You've heard a lot of talk about the Higgs boson in the high energy physics world. It's supposed to be coupled to the way mass is generated. And this machine does not have to work very well to do that. More complicated things like, well, David Gross, when he was here, I'm sure talked about supersymmetry. Finding out what is beyond our standard model is something that is going to take a little bit longer. And they're already beginning to work on an upgrade for that machine to increase its intensity. But I think we're going to start to see the physics results flowing around 2009. And we're all looking forward to it. Now, the other machine I mentioned earlier as part of the really important is an electron-positron collider. Why? Well, the proton colliders create new things mainly through the interactions of the components of the proton through the strong force. Electron-positron colliders create new things mainly through the electromagnetic, kinetic, and weak forces. It is quite possible that you can see things with electron-positron colliders that you just can't see with the proton colliders. Getting a view of whatever is new from both its strong force manifestations and the electromagnetic and weak force manifestations will tell you a lot more about what's going on. The work on what's turned into this new machine, it's got a name, it's called the International Linear Collider, has been going on for a long time. The international efforts were started by 3 lab directors, Bjorn Duke at DAISY, Hirataka Sugawara at the Japanese lab KEK, and me at SLAC. And we started it after the failure of the SSC, the big superconducting proton machine that was supposed to be built in Texas. The SSC was supposed to be international, but all the decisions were made in the United States and all the design was done in the US. And then people went out and said, why don't you come join us and put a lot of money in? We decided that with that lesson, the right thing to do was start the collaboration and have the collaboration work out what the machine ought to be, what it should look like. The target is a collider in the half TeV to 1 TeV center of mass energy range. Why so low when the proton machine is 7 TeV by 7 TeV? That sounds a lot more, but it really isn't, because the proton's a composite particle and the energy are shared among all the constituents of the protons, the quarks and the gluons and such. And for proton machines, you can talk about the mass reach. How heavy a thing could you find with it? With the first incarnation of LHC, you'll be able to look up the masses of about 1 TeV, and that's how this energy range was chosen. 2 approaches were going on in the R&D program. One was for a machine with superconducting RF cavities, another for one with room temperature. In 2004, the technology chosen was the superconducting one. We'll live to regret that, but that's another story. And an international design effort started focusing on a machine called the International Linear Collider with energy of 1 TeV. This is what the International Linear Collider is supposed to look like. There are 2 long linear accelerators. This is 30 kilometers from end to end. There's one for positrons, one for electrons. There's a collision region right here in the middle. These things are the rings where the electron beams and positron beams are generated for the next pulse. You use the spent high energy beams to generate the next one, send them down to the beginning and accelerate them again. So the final baseline gives a certain luminosity, that's the event rate, and energy, integrated luminosity, which tells you what you may be able to do, one big interaction region Hall, and two detectors in a kind of push-pull configuration so that you get some complementarity in the experimental output. It's got a schedule, and this is the wish schedule of the physics community. This is not the agreed schedule of the governments that got to put up the money. This baseline configuration, the schedule was to get that design done in early 2007. That's done. Now they're working on an engineering design called an engineering design to get the details fixed. That's supposed to be ready at the end of 2009. And then it's hoped that there will be a international agreement to start this project, and we hope, we being the U.S., that this international machine will come out easily. This is a quite expensive operation. Don't get scared of the budget. It's only money, as my wife is fond of saying. Accelerator system, 6.6 billion. This is in what's called value method. This is a way to take account of the different accounting systems used in Asia, Europe, and the US, what goes into something. So you can do the accelerator systems, essentially purchases, things made outside, personnel, and now if you turn it into US accounting, by putting in the things on the right-hand side which are not included, you end up with $16 billion. Notion is that the host will pay half of it. This kind of thing is rather expensive. We have joined an international project in thermonuclear fusion, the ITER project, which is costed in exactly the same way. The United States knew perfectly well when it took on its share of the value that it would actually cost us twice that, and we took it. Also, the half of $16 billion is less than the cost of the SSC, which we were prepared to do ourselves in 2000 when it was approved. One of the problems is to get together the international organization that's going to be required to do that. You can have the laboratories work together, and the laboratories are working together on the design, but somehow or other we are going to have to put together some sort of international group that's going to finance this and oversee its construction and all the rest of that. That is something that needs doing badly. I don't think that can start till 2010, and the Richter timeline is predicated on the timing of the election. This is a big project, and it doesn't matter who wins, the Republicans or the Democrats. The new administration for something of this scale is going to want a complete review all by itself. So the earliest that could be done is the end of 2009. And then if we're lucky, they can put together an international group in 2010. I think that's a little bit aggressive, but anyway, it's not totally impossible. There is a critical issue in all of this, and that critical issue is, will a half a TeV be enough energy? That depends on what comes out of the LHC. If the LHC finds the clues to what's beyond the standard model at relatively low energy, this will fly. If it's at relatively high energies, toward the 1 TeV end of the reach of the LHC, this machine won't fly, and it's going to have to be started at a higher energy. Already there's an effort going on to look at higher energy machines for the distant future. The technology for the higher energy machines turns out to be the room temperature linear accelerators that were rejected for the lower energy machine, which is why I say it's kind of regrettable. And there is an international group working on high gradient acceleration, which has already achieved 100 megavolts per meter at an R frequency of 12 gigahertz. Compare that to what the design of the ILC is, which is about 30 megavolts per meter. And you can see the machine is considerably more compact. Doesn't mean it's a lot cheaper. You've got a lot of stuff to work out yet to see what happens. But what will come along in 2010 is a critical decision. Is the ILC energy enough? You want me to make a prediction? I said this would be an opinionated talk. I think the answer is going to be no, and I think the higher energy machine is going to be needed. And how we get that higher energy machine, whether it's with the superconducting version expanded or with the new technology coming along with this high gradient study, I don't know about that. As I said, my bet is for something much beyond the ILC. We got to do something about the cost of these machines, because you're already talking about $16 billion for this 500 GeV machine. And even if I'm right about the benefits of room temperature technology, you're going to be talking about that much for a 1.5 GeV machine too. And what we need is new accelerator technology. Now that's come along time and time again. We started off talking about the cyclotron. Cyclotron went on for a while and reached a point where it wasn't scalable because its cost went up like the speed of its energy. That got replaced with the synchrotron. The synchrotron, the costs went up linearly with beam energy, but then all of them got replaced by colliding beams, because if you look at relativity, the reaction energy in a single machine colliding with the target at rest only goes up like the square root of energy. So we went over to colliding beams and we took another big jump. We need a jump further now, and there's work going on all over. This is just an illustration of some work that was done at SLAC. It's plasma wake field acceleration. It produced an energy gain of, let me see now, 50 GeV per meter. Not MeV per meter, GeV per meter. So at that sort of thing, if you're talking about 500 GeV, you're talking about 10 meters of accelerator. Is this going to work out? I don't know. It's early days. There's work also going on at Lawrence Berkeley Lab on laser acceleration. The laser acceleration is a little bit behind in GeV per meter, but it's the same sort of order of magnitude. It's a clear 1 to 2 orders of magnitude jump in what you can do per unit cost. The question is, can you make the beams stable enough to do colliding beams? Can you make them small enough? Can you make them intense enough? We're going to have to see what goes on in the laboratories. And this is an important piece of high energy physics, because high energy physics accelerator base is going to come to a screeching halt in 10 or 15 years, running up against a cost barrier. In the proton machine area, people are working on high temperature superconductors. With high temperature superconductors, maybe you can get another factor of 2 or 3 beyond the LHC, but you're going to run into trouble there too. Let me switch gears and talk about the dark matter, dark energy, and us business. I said that we were all startled. I was startled when I heard Saul Perlmutter give the first talk in 1999 at the Lepton Photon Conference, I gave the summary talk, and I turned aside when I talked about this one. I said, Saul, if I had the money, I'd give you the money for your satellite, for SNAP. This is very important. Berkeley is leading the effort for a new satellite to go up and find out something about dark energy. I said already, we're only 5% of the mass of the universe. There's 20 times more stuff out there. We don't know what it is. If you ask the same question only 10 years ago, then ordinary matter would have been 20 to 30% of the universe, and dark matter would have been 70%. All of a sudden, there's all this other stuff. It's a big surprise from the supernova search, and Saul and the rival group on the East Coast both have won prizes for something that I think is one of the most important pieces of physics to come along in a long time. So the 70% was a perfect surprise. The 25% we've known about for some time. And we've known about it because certain things are going on that couldn't have happened if the only thing around was ordinary matter. You could look at the velocities in clusters of galaxies. How are these things going around? Well, they were going around so fast that if it was just the mass that was in the galaxies holding it together, it wouldn't hold together. Everything would fly apart. There had to be more mass than we can't see, than we could see. The rotation curves of stars in galaxies show the same problem. And people began to think of weakly interacting massive particles, the so-called WIMPs. People have looked for them. We haven't found them. We don't know what they are. We don't know what the masses of these things are. The one thing we know is they have weak interactions with ordinary matter. To me, this is one of the most dramatic pictures I've ever seen in astronomy. What you're seeing is a collision of two clusters of galaxies, and there are three figures superposed here. One is visible light from the Hubble Space Telescope. The blue is the distribution of mass from gravitational lensing, and the pinkish red stuff is X-rays from the Chandra satellite. And what's going on here is that these two clusters are passing through each other. The ordinary matter has electromagnetic interactions as well as gravitational. It exerts a drag, and it slows the ordinary matter down and heats it up so it emits X-rays, and the dark matter keeps on racing along, and the two things are getting separate. If you wait long enough, the dark matter is eventually going to suck the ordinary matter back in. But for now, that picture, I think, is the most dramatic picture of showing the existence of this dark matter. There are a lot of other things that have gone on in astroparticle physics and cosmology. The famous WMAP data, the predecessor of WMAP, the baby WMAP, got George Smoot his well-deserved Nobel Prize this last year. This is the most perfect black-body spectrum anybody's ever seen, as far as I know. The second peak here is the first thing that was predicted by this inflation scenario. It says the universe went through a period of very rapid expansion when it was very young. There's been no real evidence for that until this showed up, and this is a prediction that was made before the data came in. I'm a little bit suspicious of postdictions. I really like predictions, and the predictions were done. The supernova experiment is absolutely terrific. This is Richter's cartoon of how the supernova experiment works. You get a binary system with a companion star and a white dwarf, and matter spills out of the binary one and spirals around and eventually falls in, and over time the mass of this one begins to go up until it reaches the threshold of 1.4 solar masses, and then it goes boom and turns into a supernova. Because it all goes up very slowly, when you reach the threshold, they're all supposed to go off at the same mass and become a standard candle. It's absolutely terrific, and the results are shown here, and what you see is a deviation from the two measures of intensity. One comes from measuring redshift, that's the Hubble distance. One comes measuring the absolute intensity, and you got 1 over r squared, that's a different distance. And you can ask from the two of them, are they consistent with the universe that's in uniform expansion? And the answer is no. You have to say the expansion of the universe is speeding up. Sorting this out is, I think, one of the most important experiments to be done in particle physics. Note that particle physics is a field which subsumes other fields. It's got a variable threshold. Particle physics is whatever you can do with the highest energy you've got, and particle physics is whatever you can do to understand the very small and the very large. So, Francis, you didn't know about your role in particle physics, but that's what you're doing. What's coming next in this field of astroparticle cosmology? A new satellite glass for high energy gamma rays is supposed to go up next May. Thank God it is not on the shuttle. It's on a free flyer, so we only have to worry that the Defense Department doesn't steal our rocket to launch a spy satellite, but that doesn't look like what's going to happen. Planck is the next generation from COBE to WMAP to Planck, a next generation cosmic ray background, microwave background observer that's also going to look at polarization. And the polarization of a microwave background can tell you a lot about the early universe. The Large Synoptic Survey Telescope, a ground-based telescope of a special kind that's good for gravitational lensing and can contribute to understanding the dark energy thing. And something called JDEM, the Joint Dark Energy Mission, is an extended supernova search. Joint means it's supposed to be a DOE NASA thing. GLAST was the first DOE NASA collaboration, and one of the things I'm proud of is I sold it to Berkeley. First time DOE and NASA had ever done anything together. A Joint Dark Energy Mission has been given the highest priority for the so-called Beyond Einstein probe by a recent National Academy study. There's going to be an announcement of opportunity, the way the NASA people do it. They'll say there's an opportunity to do something for studying dark energy. Send in your proposals. Berkeley has the lead in a project called SNAP. They've been working on it for a long time, and I think that they're going to end up winning, and if they don't win, it's all their own fault, because they certainly have had more time to think about it than anybody. I hope that it all comes. Neutrinos. I want to mention a little bit about neutrinos. It's a hot topic starting into the 90s, in the 1990s. We know that there are 3 kinds of neutrinos. We know that for a long time. Neutrinos have mass. We didn't know that. 20 years ago, we didn't have a clue that neutrinos had mass. The standard model of particle physics has no mechanism to generate neutrino mass. You can have neutrino masses, but you've got to paste something extra onto the standard model. And there's a lot of argument about what that is. So what we found out is that neutrinos have mass. They can change identities. Type A neutrino can turn into type B neutrino, can turn into type C neutrino, and can go back and forth. And Ray Davis and Masatoshi Koshiba shared the 2002 Nobel Prize for it. This is Ray Davis in the Homestake mine with his 100,000-gallon container of cleaning fluid. It's a remarkable experiment. It's full of chlorine. And neutrinos can interact with chlorine and turn an atom of chlorine into an atom of argon. And once a month, Ray Davis would filter all of this stuff and look for, I think, 5 atoms of argon out of 10 to the 27th atom of chlorine. And he didn't find enough. And one of the problems was if there was any inefficiency in his extraction of argon, there wouldn't be enough. There would be a neutrino deficit from inefficiencies. So was his neutrino deficit real or not? It took a couple of other experiments to confirm it. This is the detector called Super Kamiokande. It is 50,000 cubic meters of water. It is a huge, enormous thing, and what you see here is it partly full, and experimenters going around in their rubber boats, getting all of the photomultipliers, lining the walls, plugged in, and connected up as they fill the thing. I think this is really quite something. Very dramatic picture. I sort of love that one. And from the experiments done with Super Kamiokande's predecessor and Super Kamiokande itself, the cosmic ray muon neutrinos were found to be able to change into something else. The electron neutrinos were disappearing somehow from Ray Davis's work, and now you knew that the muon neutrinos were disappearing too, and this has led to an explosion of effort at accelerators, at reactors, underground, with radioactive decay. And there are a couple of experiments coming along that I think are going to be very important. And there's one recent one that I think was a disappointment, but I may be discreet and not talk about it. I borrowed this slide from Friedman. He chaired the Committee on the Future of Neutrinos, and I love it. Given the appropriate resources, the future of neutrino physics is bright indeed. All I have to say is that those trunks aren't big enough for the future of accelerator-based high-energy physics, but they're plenty big enough for neutrinos. The thing I think one of the most important experiments coming along is a reactor experiment. It is being done in China, of all places. This is Gaia Bay. Gaia Bay, when this thing comes on, will have 3 big reactors running, and the notion here is to look at the way those neutrinos interact in their detector, and to look at a number of events of various types. What's being looked for here, is a parameter which doesn't mean anything to you. It's called theta 13. It is a very critical parameter because if it's too small, it becomes impossible to do CP violation in the neutrino sector. All we know about theta 13 from existing experiments now is that it's sine squared 2 theta 13 is less than 0.1. If it's less than 0.01, which is the reach of the Gaia Bay experiment, I don't think we'll ever see CP violation in the neutrino sector. Another experiment that's very important I don't have a good picture of. It's to answer the question of, is a neutrino its own antiparticle? Is it a Dirac or Majorana particle? That's an underground experiment. There are 2 competitors doing prototypes, and those competitors are going to each have a I think it's a few percent scale detector built and running next year, and then we'll see what the backgrounds really are for them and which ones should get scaled up all the way. The one I'm disappointed in is the one called Mini Boom. There was an experiment done at Los Alamos 10 years ago, and that experiment implied that maybe there was a fourth kind of neutrino, and that kind of neutrino had different interactions, and the results sat there. I never believed it. I had very particular reasons why I thought that experiment was wrong. And Mini Boon was done to show what happened. And I said this was an opinionated talk, so I'll give you my opinion of it. What you see here is the number of events that they had compared to what the model said they should have. If you look at the low energy, you see that the real number of events are much bigger than the model. Although they claim to be doing what's called a blind analysis, where they wouldn't do anything with the results till all the data was in. By the way, I think that's a very poor idea too. When it turned out this way, they changed the energy range that they would use to the energy range above the dashed line. The probability that the data that as is there fit with any of their hypotheses was less than 1%. So they changed the cut on energy to make it better. But then comes another problem. Most people who do statistics don't really recognize that if a fit is too good, there's something wrong with your experiment. And after they did their cut, then what they did is they looked to see whether there was this other kind of neutrino, and the answer is 0. But the data is so good that it also has only a 1% probability of being right. And I don't see how one experiment that's based on two 1% probability distributions can say anything about whether the basic thing, the basic LSND experiment was right or wrong. As I told you earlier, I believe it's wrong. I think it's time to bring this to an end, and I want to bring it to an end with a picture. This is a picture looking toward the center of the Milky Way. The little white dashed line you see there is an airplane going overhead, and the shadows in the lower left and the lower right are trees. Why do I show this? Well, I have to think back to how I got into physics. When I was growing up, it was dark outside, not the way it is now. And when it was dark outside, you could look up into the sky and you could see the galaxies. And you could see the Milky Way. You could see this band of diamonds right across the sky. And it was fascinating, and that's what got me to think that what I wanted to do when I grew up was to find out how the universe worked. Well, I've made my contributions to help find out some of the things about how it's going to work, but there's still a lot more to find out, and I wish that the young people today could look and see what I saw with my own eyes. You can't do that, but I hope you look at pictures like this one and say, I want to help find out what makes the universe work. Thank you all.
Okay, well, that was wonderful. Do we have questions from the audience? We will do our best to pass around microphones so that everybody can hear the questions.
I want to ask two naive questions.
Uh-oh.
The first one is the linear accelerators were made to avoid Cherenkov radiation going in a circle. But then after they built the linear accelerator, they store the particles in a circle at the end of the machine anyway at Stanford. So it seems to defeat the purpose of making it a straight line. Then I noticed the new linear accelerator is back to a straight line again. It seems a contradiction. The other question I want to ask is why the picture of Segre is an empty circle.
Well, actually I have one of Emilio's last books on my desk. It's a book he wrote about the great classical physicists, and I should have snatched a picture from it and put it in for the start of the Segre lecture, but I didn't. As far as the other thing goes, you're not looking at the relative energy. What has happened is the slack linear accelerator can produce a beam that's 60 billion electron volts. You can't put that in something that is much smaller than that LHC machine, 20 kilometers around. What was done very early is on the storage ring I built to do physics with some of my distinguished colleagues here. There's some Goldhaber, Willie, Janowski, and such, was 3GeV, and some people came up to me and said, we're going to revolutionize condensed matter physics if you will let those blasted X-rays out. So we built them a port, and then we let the X-rays out. And what you have is all the synchrotron light sources. The SLAC source was the first of the modern light sources. It has done just what they promised. It revolutionized condensed matter physics, molecular biology, structural biology. It's being used for environmental science. And what was a plague to the particle physicists is gold dust to the synchrotron regulation. So it's a really nice outcome.
I have to comment on the empty space that you saw, because I don't know if Nathan is still here, but I will introduce my speculation as to why we had that empty space. Is that it's honoring Segre, but it's also pointing to the future and all the possible future Nobel Prize winners that we're going to have.
Terrific. That's why she's chairman of the department. I think you've got to put her on the chancellor's list, too.
Other questions from the audience?
Okay, you all believe exactly what I said, and you're going to do just what I told you to. I see a doubt or two from the theorists.
Well, we all love the fact that you brought in both the astrophysical aspects as well as the particle one. So.
And then there's your chancellor, too. And Bob Kahn is looking very restless.
The way I understand it, I'm delighted to be corrected, that when they did this experiment with the supernova class 1A, comparing its redshift with its apparent brightness or its intrinsic brightness, using it as a standard candle, there was a disparity. And out of that disparity, suddenly we had an accelerated universe. Why didn't they first consider that perhaps not all redshifts are cosmological, or there's something wrong with our conception of the standard candle? I just want to know how you are so sure. No, I want you to explain, why are you so sure that the universe is accelerating?
This is not really my bag. And I can tell you, though, that there was a considerable amount of skepticism about the standardness of the standard candle. There was a lot of work done by a lot of people. The biggest question was dust. Was there dust that was absorbing the light? Because if there was, it would dim the light and you get the wrong answer for the brightness. That went on for several years, and the experts in the business finally concluded that that could not be it. So, with a big amount of work, came to the conclusion that it was standard enough. The deviations are sufficiently large, so it doesn't have to be perfect. And the next experiment is supposed to be able to look to much bigger distances, much higher z's, where the deviation will be still larger, and then maybe we'll be able to make some quantitative statement about what's going on. If the answer comes out a certain way, then Einstein's cosmological constant is consistent with what we're seeing. If the answer is different from that, then it's got to be something else. And from what we know now, it's pretty close to the answer that the cosmological constant would give. But the error bars are still big enough to lead to something. Ah, now you want me to really be prejudiced. If there's a Higgs boson there at an accessible mass range, that's up to a few hundred GeV. That's the range that most of the theorists say it has to be in. I think they'll find that no later than a year or so after the machine comes in. Just because its luminosity is so enormous. As I say, it only has to work at a few percent. I think that supersymmetry is one of the silliest ideas ever. Supersymmetry, to solve two little problems in particle physics, puts together a theory with 124 new arbitrary constants. Now, that's not the way we made progress in science up to now. We try and reduce the number of constants. Sometimes we have to increase it. You know, when the Greeks thought that there were only 4 elements, and we had to run up the number of elements, and people didn't think that there was a weak force or a strong force until until the 20th century, so we had to increase those too. But it just seems that that's to be a little bit too gross. If you want another thing that I think is really one of the silliest things ever, it's the landscape. I talk to the string theorists in the following way. I say that they've got 3 years. And they say, why 3 years? I say that string theory was invented 37 years ago, and Moses led the Israelites in the desert for 40 years. You've got 3 years. The landscape is empty of any predictive ability. The landscape says there are, I think it's e to the 200 possible solutions to string theory, and they're all equally probable. And I said to them, look, give me a little help. You don't have to pick out the right one, but show me a correlation. Show me that if the electromagnetic coupling constant is anywhere around where it is that we see it, that the weak coupling constant is also someplace around where we see it. Is there a ridge in your landscape? The answer I've got is we don't know, and we don't know how to tell. I think that what we need is the experiments. I'm hoping for some real excitement for the LHC. I don't know what's going to come out. I would love the most oddball solution, which is micro black holes, which say more dimensions. I think that would be really neat.
Two quick questions. Why are you shutting down SLAC and Fermilab at the same time? Second question, what's the probability of the International Linear Collider coming to this country?
The first question has to do with money. And it has to do with what kind of progress you can make in a machine. An accelerator has got what I call a natural data doubling. If you're going to make something significant happen, you really need to reduce your error bars by a factor. That's the data doubling. The B factory at SLAC and the machine at Fermilab are shutting down for somewhat different but related reasons. The B factory at SLAC data doubling time has gotten to be so long that without a major upgrade to increase its luminosity by a factor of 10, there's no point in going on with it. Fermilab is facing the pressure from the LHC. Anything that you can find at Fermilab, you can find at the LHC. And because the LHC has both more energy and 100 times the design luminosity, it doesn't take very long to do it. So you needed something new at Fermilab too. The thing that is sort of regrettable is that we're so slow on the linear collider that we're not already doing it. Now, will it come to the U.S.? I think what you're asking really is, I call it a political science question, not a science question. It is not so expensive that we can't afford it. We certainly could afford it. When the time comes to make the decision, will we want to afford it? Beats me. It depends on who is president. Now, I don't know what Ms. Clinton thinks, but President Obama comes from the state where the where the ILC might be built. So I think if you want to bet, then you might want to bet on that one. But when you come down to it, there has not been the resources to do the kinds of upgrades needed at those laboratories to keep the U.S. accelerator program on the frontier. Interestingly enough, the U.S. Advanced Accelerator Program is probably the leading program in the world. You take SLAC, what goes on here, what goes on at some of the other laboratories where there are electron machines, and those are the leading programs in the world. If we actually pull off an effective 50 GeV per meter technology, it will be because of the work that's going on in the U.S., as long as they keep funding that. But at least that's relatively cheap. Thank you. I will make sure I get the credits right the next time.
I'd like to ask
one over there. Dark matter is what? Hadrinos come, hadrinos go. I don't know what they are right now. The theorists are good at inventing new things. One of the problems that theorists have lived with since the mid-70s is the lack of any data saying where they should be going. The only thing that's disagreed with the standard model are the neutrino oscillations, and I think that one wouldn't call the acceleration of the expansion disagreement with the standard model, because that model never had anything to do with gravity. So I don't know what a hadrino would be. But I can give you a list of things that they are inventing that might or might not be it. I hope that the LHC tells us. I ducked your question.
I'm curious, is there any role for non-accelerator based high energy physics like cosmic rays?
Sure. I thought I gave you on my list everything except the first was non-accelerator based. I talked about experiments in space. I talked about experiments with reactors. I talked about underground experiments. The non-accelerator based high energy physics program is alive and flourishing. There's a huge amount to do. The problem in particle physics, I'm going to call it particle physics now, is a problem with the accelerator-based program. The accelerators have been the driving force in deepening our understanding up until relatively recently. And now they've reached a point where they're simply so expensive that it's hard to get one built. But there are lots of things being done, and there are lots of things going on here and up on the hill and at SLAC and at other places that are non-accelerator based particles.
What's your opinion of what will come out of these experiments in which a couple of heavy nuclei are smashed together in order to look at the quark-gluon plasma? I've seen articles on that recently and have some collaborators or colleagues who actually are working on that.
I haven't paid a lot of attention to actually what they're going to find out about it. I think they're going to find out more about the distribution and interaction of the partons that make up the protons and neutrons. I don't think that they're going to be pushing on into what's going on at still smaller distances or still higher energies. I could turn out to be wrong. Some of the people claim that the information that they get from those collisions is critical to understanding some of the things that will turn up at the LHC, but I haven't really studied it, and I can't give you any educated answer.
Okay, I think we should call it an evening and thank Dr. Burt Richter one more time.
Thank you.